All right. Next talk in the session will be on how to compute call graphs for the Android implementation of WhatsApp. It'll be given by Ákos.
Cool, yeah. Thank you for the intro. I'm Ákos. I work at WhatsApp, and today I'm going to give a talk on how we use the Callgraph Reachability analysis in order to improve the health and the performance of the Android app. So this work pretty much started with a request from the Android app health team, who came to us and asked, can we find instances where certain performance critical functions end up potentially transitively calling computationally expensive functions? Like, for example, they are doing something on the UI which checks something and then it reads from some database which is potentially slow. They wanted to flag these kind of cases. And we said, yeah, probably we can do something about it. For this, we need two main things. One is the specification. So we need to know what is exactly performance critical and what is computationally expensive. And then we need an analyzer which is automated and fast enough to give feedback on code changes at the scale of WhatsApp. So in theory, this is a relatively well-known and well-studied problem. It's called reachability analysis, where you have a set of sources, a set of sinks, potentially some sanitizers as well, and you want to check whether there is control flow from source to sink without going through any sanitizer. This is slightly different from some of the previous talks today, where they were about taint analysis, where you're mostly interested in tracking data. Here we are mostly interested in tracking the control flow. But one common point is that we also employ call graphs. And in particular, an approximate solution is to use the static call graph. In one of the previous talks, there was a lot of discussion about the different precision of call graphs. In general, this method can work with any kind of call graph. For now, in the current implementation, we use a very basic static call graph, which is based on the static types of the program. So basically, if you have something like this, where you have some sources, you have some sinks, you have some sanitizers, then, for example, this path on the red is something that you would want to report and flag. But, for example, this blue one is fine because it goes through a sanitizer. Now, how do we do this in practice? So we turn to our in-house static analysis platform, Infer. It's developed at Meta. It has been running for more than 10 years, finding thousands of bugs every month at a large scale. And Infer supports multiple languages, including Java and Kotlin, which is great because that's what WhatsApp Android is primarily written in. And it also has a bunch of checkers related to all sorts of properties, including memory safety, data races, deadlocks, temporal properties, but it also had a checker which was called annotation reachability, so it was a very good candidate to look at. And as its name suggests, in annotation reachability, the specification can be done using Java annotations. So, for example, I can mark my performance critical and expensive functions in the code using Java annotations, and then in the configuration file of Infer, I could say like performance critical is my source, expensive is my sink. So that's how we can specify these functions. And how do Infer checkers work? Well, Infer checkers are modular. They analyze one procedure at a time independently. They mostly use abstract interpretation, so they propagate some abstract state in an abstract domain through the function or procedure in order to obtain a summary. And it's compositional, which means that this summary that we obtained can be used in different calling contexts. So if there's a function which is being called in different contexts, we don't need to analyze it multiple times. We can substitute this summary in every calling context. And it's on demand, which means that dependencies are analyzed as needed. This will be interesting when when we see recursion, but I will get back to that later. So for example, if we have some function foo that we want to analyze, but it calls function bar, then we first analyze bar, come up with a summary, put it in our database so that we can reuse that to compute the summary of foo. So this is how Infer checkers work typically. And for annotation reachability, I will first go through an example. So we have this example from before, and here you can see the dependency between the functions. So first, Infer would analyze read from database, which from the perspective of this checker, it doesn't do anything because it doesn't call any function, so it will just provide an empty summary. Then we go to check something where we see that in line 7, it calls this read from database function, which is actually a sync annotated with expensive. So we put this in our summary. And then when we go to something on the UI, we see that we call check something in line 3, which itself is not a sync, but there is a sync reachable from it, namely read from database, which is expensive. So we put this information in our summary. And finally, what we see is we have a function, something on the UI, which is marked as a source, performance critical, but its summary says that it calls something which is expensive. So this is something that we would report as an issue. And we can also reconstruct the path by traversing these summaries in the other direction. So just to formalize this a little bit, in the abstract domain of this annotation reachability checker, the abstract state of a function f is a set of these GNHE tuples, which basically mean that in the current function that we're analyzing, f, at line n, we call a function g, which eventually reaches some function h, which is annotated as a sync with the annotation a. So basically, in every summary, we are storing just single steps towards the sync. And initially, we start with the empty state. We traverse the instructions of the function in order. And the way the transfer function works is that if we see some call to some function g, then we check if g itself is a sync. Then we add an entry that we directly call a sync. But if it's not a sync, then we check whether it can reach any sync. And if yes, then we add like a so-called indirect entry. And we also check for sanitizers as well. And interestingly, the join operation is simple set join, and the summary is the state at the exit of the procedure. So this means that this is both flow and path insensitive, which means that in some sense it's over-approximate because, for example, we would report calls that are guarded by infeasible conditions, but it's also under-approximate, for example, if there is a dynamic dispatch or lambdas involved. But in our context, what was really important is to be scalable and to find meaningful bugs with a relatively low false positive ratio. So we are fine with making these trade-offs. And now this checker was mostly working well for our purposes, but we did have to make a few extensions. One of them is to support the specification of function via regular expressions, primarily because we had external code that we wanted to annotate, and we can't really go in and modify the source code. But it also allows us to express our properties in a more compact way. For example, in one of the properties, they wanted to say that every UI event handler is a source. So basically, you could just say that if it matches some regular expression over some base UI class, then every derived function should be treated as a source. But this also opened up the opportunity to support other languages which doesn't have annotations. And another thing that we did is minimization. So in general, nothing prevents a source from calling another source or a sync calling another sync. So we came up with these concepts of paths being source and sync minimal, with the idea being that, for example, here if you somehow eliminate or you break the chain in the middle, then you solve all the extended issues as well. Now, how does this? So what did we do in practice for WhatsApp Android? Basically, we collaborated with the app health team, and we came up with 2 properties, which together use 8 annotation and 11 regular expressions. In the first property, the sources are performance critical functions, typically things that happen on the UI, so UI event handlers. And sinks are computationally expensive functions, worker threads, or file I/O operations. And we also had some sanitizers. These are typically features that are not shipped in production builds. So for example, tests or debug utils or like these Java precondition checks. And there was another property as well, where the sources and the sinks were based on threading annotations that are incompatible. So I think it was the source is worker thread and the sink is a main thread annotated function. Those should not be called directly, so that was another property. And to break it down a little bit, you can see the 2 properties, and you can see how many source, sink, and sanitizer annotations we used, how many regular expressions we used, and we also have some data on the coverage in terms of all the procedures or functions that you have in WhatsApp Android code base. I put these relative numbers because of confidentiality, but the key point here is that WhatsApp Android has multiple hundreds of thousands of functions. So even if you see percentages like 1 or 0.2%, that is still multiple hundreds or multiple thousands of functions. So this is like a non-trivial number of sources and sinks to be analyzed. And for the second property, we have a higher number because that reused more of the existing threading annotations that were already there in the code, whereas for the first property, these annotations were mostly put in the code just for the purpose of this particular check. And so the way software development and static analysis typically works at Meta and WhatsApp is that we have the developers who submit code changes. At Meta, we call these diffs. You can think of it as a lightweight pull request. Basically, every commit needs to go through a review process. So it's like a unit of code change. And here we have the human reviewers who can accept the change or write comments. And at the same time, we also have CI running with tests, static analysis, and all sorts of checks. And this is where, for example, Infer would report this bug. So if you would submit this example, then Infer would tell you that you have this problem with performance critical calling the expensive function. And then we also have a trace. Infer would show you how exactly you end up going from the source to the sink, which was very important because in production, a lot of the examples that we saw had often traces of length of more than 20. So this was very helpful for developers, and they could click them through in an interactive way. And once the reviewer comments come in and also the signal from static analysis, then the diff goes back to the code change goes back to the author, so they can submit a new version. And let's assume that they fix, all the problems flagged by static analysis, all the problems flagged by the reviewers. Then after some point, the code gets merged into the main branch, and we still have a continuous CI running periodically on the latest revision. And if it finds any problems, then we have the option to file tasks either fully automatically, manually, or in a semi-automated way, and assign them to the developers. Why is this needed if we already have the analysis during code change time? Well, sometimes developers ignore the signal, so bugs can slip through. Also, on code changes, we want to be much faster to give fast signal to developers. So typically the analysis that we are doing is more shallow, whereas in these continuous periodic runs, we have much more time, much more resources, so we can do deeper analysis. And it is also possible that you have two code changes which are individually fine, but then once they get merged, they have the bug. So this is also another line of defense. And the way we deployed it is first we checked with the periodic runs. We wanted to see how many pre-existing issues there are there in the code base, what's the quality of the reports, and what's the volume, because if we have too many issues, then developers would simply just not care. And we found that without any minimization, we have 12,000 issues. And after fixing a few obvious false positives, the signal quality was actually quite good. These were mostly true positives. However, it was still too large, like, okay, which ones do you fix, like where to focus? So we applied source and sink minimization, and we found that sink minimization already reduces the number of issues by an order of magnitude, and this is actually quite a manageable level. So we decided that source minimization is not needed. And in addition, usually the sources are closer to the actual business logic, whereas sinks are often down in low-level libraries or utilities. And in general, developers are much more comfortable fixing code that is closer to the business logic or closer to the code that they own. And so after we were happy with the quality, then we started to roll out this on every code change, first in a so-called shadow mode, where the analysis was already running for every code change, but the developers did not see any signal. It was only us who saw the signal on some internal dashboards, so we could see exactly what would the tool report on which code change. Then we had a group of early adopters, and then we had the full rollout. And so to give some results, in terms of the pre-existing issues, we filed around 60 tasks in a semi-automated way. And so far, in the first 3 months, I think, up until the paper was written, 7 have been fixed, which is not a huge number. In general, this was sometime in the beginning of the year, so that's not really the season where people fix pre-existing problems. However, some of them we could relate to actual production data, and there was one particular example which was related to crashes happening in production. ANR is app not responding. I think it's when the app doesn't respond for like 5 seconds and the operating system kills it. So there was this example which could directly be linked to these production ANRs. I think what happened there is there was some eligibility check for a feature that was only enabled in certain regions, and this was running on the UI thread. So on the one hand, it was not necessarily to do for every WhatsApp user, and on the other hand, even for those users who were in those regions, this should not be done on the UI thread. And so the engineers seen the issue, they fixed the problem, and then they did a controlled experiment where the fix was already rolled out to some users, and it was not rolled out to the other set of users, and the number of app not responding crashes were reduced by 0.5%, which again doesn't seem like a huge number, but considering that WhatsApp has more than 2 billion users, this is actually quite a big number. And it also made chat loading speed up. It also made chat loading for everyone 1.25% faster, which again, at a scale of WhatsApp is actually a considerable win. And as I said, we also rolled this analysis out for code changes. And in the first 3 months, Infer has reported around 170 problems, out of which 90 were fixed. So it's like the fix rate is slightly above 53%, which is quite typical for the static analysis that we are doing it in Meta or WhatsApp with the other kind of issues. So we were also quite happy about it. We did look at some of the unfixed issues to see what's happening there, and we found quite a few interesting categories. One was related to Kotlin conversion. So when you convert a module from Java to Kotlin, then basically Infer would report this as so you move the pre-existing issues and Infer would report this as new. Infer does have some heuristics to match issues, like for example, if lines are shifting, then it wouldn't report the same issue as being new, but converting to a new, like a different language was beyond the scope of these heuristics. Another interesting case was related to mutual recursion and scheduling. So as I mentioned, Infer has this modular analysis where it needs to analyze dependencies first. Now, what happens if there's a mutual recursion? Well, you can either do a fixed point computation, but Infer doesn't do that. It just simply unrolls to a depth of 1, which essentially means that it cuts the dependency graph until it becomes acyclic. And so what happens here, for example, in this example, is if you cut the edge from G to F, then you would see the issue. But if you cut it from F to G, then there is no path from source to sink, so you don't see the issue. And the scheduling in Infer can sometimes be non-deterministic, especially if the code changes. So what happened is that on every code change, Infer is run twice, one on the parent revision and one on the current revision to compute the change in the issues. And what happened sometimes is that there was a different scheduling in the parent and in the current. And if the issue was not found in the parent but was found in the current, then it was reported as a new issue. And for that, we switched to a new, like a different scheduler, which is more deterministic. And finally, some other false positives were related to flow and path insensitivity. So, for example, we have seen instances where a call was guarded by some flag which was only enabled in debug builds. So these were false positives. And we have also seen examples where we would have needed flow sensitivity, where basically the sanitization happened in a way where developers called a particular function to start a block which they considered as sanitized, and then finally they called another function to end this. Just a few words about performance. In general, it's quite hard to measure because in production we have caching, we have multiple checkers, Infer is running in parallel. But in general, the continuous analysis that runs periodically, it takes 33 minutes to compile the entire WhatsApp Android and around 50 minutes to analyze, out of which if you only run reachability is 15 minutes. And on code changes, the total time, including the 2 runs for the parent and the current with all the checkers, but only limited to the change files and their dependencies, is around 30 minutes. So the key takeaway here is that this analysis is fast enough to run multiple times in continuous mode, and it can also provide timely feedback to code changes. And in general, reachability is not the bottleneck. There are much more expensive checkers in Infer. So yeah, thank you. And if you want to learn more about the other kind of code analysis that we do at WhatsApp, then you can check out my website.
Thanks, Ákos. We have time for a quick question. All right, I had a question over here. So when you mark these methods, or I suppose you asked developers to mark methods as being expensive, the sinks, how much pushback was, well, I wonder, the pushback is perhaps the second question. How much effort did it involve?
So the good thing is that there is a dedicated team for app health. So there is a team who's particularly responsible for the health of WhatsApp Android, and they were quite eager to put in all these annotations, but also having these regular expressions helped a lot to annotate code at a large scale in a concise way. So there was a considerable amount of effort, but yeah, we had help to do that. And we have also seen examples where, for example, the app health team started to put in all these annotations, and then engineers outside of the app health team, they see that oh, we have now these annotations and we can find these kind of bugs. This is super useful. Let me put in some annotations into my own modules. So we have seen these kind of examples, which was very nice to see, because yeah, often in practice it's hard to motivate developers to to use annotations and to use specifications, but here they were quite eager about it. I think it's also related to the fact that in the past 2 years there have been some issues with the app health quality, like more and more crashes. So quality is a top concern nowadays. So even coming from higher above in the company. So yeah.
Thanks a lot. Thanks a lot for the presentation. I think maybe I missed something when you mentioned the Kotlin problem towards the end. You said that there is no fixed point computation for the cycle, and I missed this part. Is it a soundness limitation that you just decide to have and that's okay, or is it, or did I miss some reason why it was sound?
So that's actually 2 separate problems. The Kotlin problem is when you have a Java code and you convert it into Kotlin, then basically you had one issue which disappeared, but then you have another issue which appears in a different file with different name, different code. But in theory, it's the same issue. You just move it from one implementation to the other. And Infer is not that smart about figuring this out. But at the moment, we can live with it because usually this doesn't just affect Infer. It also affects all the other static analysis and linters. So when people do these kind of conversions, they usually expect that since it's a new file, they will see issues that are pre-existing. The other thing related to the recursion is again something which at the moment we don't have fixed point computation, which means that with this deterministic scheduler we mitigated the problem in the sense that the issue is either found or not found, but it's at least deterministic. So if we do 2 runs, one on the parent, one on the current, they will agree, and we won't report an issue as if it was new, or we won't report an issue as if it disappeared. However, it is true that we might completely miss issues, but this is something that at the moment we accept.
Okay, thank you. Actually, that brings me to another related question. I know that Meta also has another tool for taint tracking, which is Zoncolan analyzer by Francesco Logozzo. And when you started the presentation, I was very much expecting you would come towards this tool, which, if I understand well, does not have this limitation with fixed point. So did you think or compare the two and try to think about which one would be the most adequate? What are the reasons why you went towards Infer?
The primary choice behind Infer was that here we are mostly interested in tracking control flow and not data flow. And I think Zoncolan is mostly targeting data flow with the taint analysis. And in Infer we already had this checker, annotation reachability, which was doing kind of exactly what we wanted. We needed to do a little bit of extensions, but it was more or less fit as is off the shelf, and it was tracking control flow. So, and this checker was actually a couple of years ago developed to solve similar problems in the Facebook Android code base. However, after some time, people started to get somehow less interested in the problem. Maybe they didn't have like a dedicated team responsible for the app health, but I do know that it helped during some conversions there as well, like I think when they were modernizing the feed. But yeah, for us it came out to be very useful as is off the shelf. But yeah, I mean, it would probably be useful to take a look at Zoncolan to see if it can do any control flow analysis as well, and then compare.
All right, perhaps we can take the remaining questions offline. Let's thank Ákos once again.